Aggregation. Data cubes and materialized views. Not every data warehouse is necessarily a column store. Traditional row-oriented databases and a few other architectures are also used. However, columnar storage can be significantly faster for ad hoc analytical queries, so it is rapidly gaining popularity. Another aspect of data warehouses that is worth mentioning briefly is materialized aggregates. As discussed earlier, data warehouse queries often involve an aggregate function, such as count, sum, AVG, min, or max in SQL. If the same aggregates are used by many different queries, it can be wasteful to crunch through the raw data every time. Why not cache some of the counts or sums that queries use most often? One way of creating such a cache is a materialized view. In a relational data model, it is often defined like a standard virtual view, a table-like object whose contents are the results of some query. The difference is that a materialized view is an actual copy of the query results, written to disk, whereas a virtual view is just a shortcut for writing queries. When you read from a virtual view, the SQL engine expands it into the view's underlying query on the fly, and then processes the expanded query. When the underlying data changes, a materialized view needs to be updated, because it is a denormalized copy of the data. The database can do that automatically, but such updates make writes more expensive, which is why materialized views are not often used in OLTP databases. In read-heavy data warehouses, they can make more sense. Whether or not they actually improve read performance depends on the individual case. A common special case of a materialized view is known as a data cube or OLTP cube. It is a grid of aggregates grouped by different dimensions. Figure 3-12 shows an example. Figure 3-12, 2 dimensions of a data cube, aggregating data by summing. Imagine for now that each fact has foreign keys to only 2-dimension tables in Figure 3-12. These are date and product. You can now draw a 2-dimensional table with dates along one axis and products along the other. Each cell contains the aggregate, e.g., sum of an attribute, for example net price of all facts with that date product combination. Then you can apply the same aggregate along each row or column and get a summary that has been reduced by one dimension, the sales by product regardless of date, or the sales by date regardless of product. In general, facts often have more than 2 dimensions. In Figure 3-9 there are 5 dimensions: date, product, store, promotion, and customer. It's a lot harder to imagine what a 5-dimensional hypercube would look like, but the principle remains the same. Each cell contains the sales for a particular date, product, store, promotion, customer combination. These values can then repeatedly be summarized along each of the dimensions. The advantage of a materialized data cube is that certain queries become very fast because they have effectively been pre-computed. For example, if you want to know the total sales per store yesterday, you just need to look at the totals along the appropriate dimension, no need to scan millions of rows. The disadvantage is that a data cube doesn't have the same flexibility as querying the raw data. For example, there is no way of calculating which proportion of sales comes from items that cost more than $100, because the price isn't one of the dimensions. Most data warehouses therefore try to keep as much raw data as possible, and use aggregates such as data cubes only as a performance boost for certain queries. Summary. In this chapter we try to get to the bottom of how databases handle storage and retrieval. What happens when you store data in a database? And what does the database do when you query for the data again later? On a high level, we saw that storage engines fall into 2 broad categories: those optimized for transaction processing OLTP, and those optimized for analytics OLAP. There are big differences between the access patterns in those use cases. OLTP systems are typically user-facing, which means that they may see a huge volume of requests. In order to handle the load, applications usually only touch a small number of records in each query. The application requests records using some kind of key, and the storage engine uses an index to find the data for the requested key. Disk seek time is often the bottleneck here. Data warehouses and similar analytic systems are less well known because they are primarily used by business analysts, not by end users. They handle a much lower volume of queries than OLTP systems, but each query is typically very demanding, requiring many millions of records to be scanned in a short time. Disk bandwidth, not seek time, is often the bottleneck here, and column-oriented storage is an increasingly popular solution for this kind of workload. On the OLTP side, we saw storage engines from 2 main schools of thought: the log-structured school, which only permits appending to files and deleting obsolete files, but never updates a file that has been written; Bitcask, SS tables, LSN trees, LevelDB, Cassandra, HBase, Lucene, and others belong to this group. The Update and Play School, which treats the disk as a set of fixed-size pages that can be overwritten. B-trees are the biggest example of this philosophy, being used in all major relational databases and also many non-relational ones. Log-structured storage engines are a comparatively recent development. Their key idea is that they systematically turn random access writes into sequential writes on disk, which enables higher write throughput due to the performance characteristics of hard drives and SSDs. Finishing off the OLTP side, we did a brief tour through some more complicated indexing structures and databases that are optimized for keeping all data in memory. We then took a detour from the internals of storage engines to look at the high-level architecture of a typical data warehouse. This background illustrated why analytic workloads are so different from OLTP. When your queries require sequentially scanning across a large number of rows, indexes are much less relevant. Instead, it becomes important to encode data very compactly, to minimize the amount of data that the query needs to read from disk. We discussed how column-oriented storage helps achieve this goal. As an application developer, if you're armed with this knowledge about the internals of storage engines, you are in a much better position to know which tool is best suited for your particular application. If you need to adjust a database's tuning parameters, this understanding allows you to imagine what effect a higher or lower value may have. Although this chapter couldn't make you an expert in tuning any one particular storage engine, it has hopefully equipped you with enough vocabulary and ideas that you can make sense of the documentation for the database of your choice. Justin Sheehy and David Smith, Bitcask, a log-structured hash table for fast key/value data, Basho Technologies, April 2010. Jeffrey Dean and Sanjay Gemawat, LevelDB Implementation Notes, leveldb.googlecode.com. Fei Chang, Jeffrey Dean, Sanjay Gemawat, et al., Bigtable, a distributed storage system for structured data, at 7th Usenix Symposium on Operating System Design and Implementation OSTI, November 2006. Adrian Grand, What is an Lucene Index? At Lucene/Solar Revolution, November 14, 2013. Deepak Kandapit, Hacking Lucene the Index Format, hackerlabs.org, October 1, 2011. Operating Cassandra, Compaction, Apache Cassandra Documentation v4.0, 2016. Rudolf Bayer and Edward M. McCrate, Organization and Maintenance of Large Ordered Indices, Boeing Scientific Research Laboratories, Mathematical and Information Sciences Laboratory, Report No. 20, July 1970. Howard Chu, LDAP at Lightning Speed, at Build Stuff 14, November 2014. Mark Callaghan, Choosing Between Efficiency and Performance with RocksDB, at CodeMesh, November 4, 2016. Igor Canetti, Seeing Dawn, and Mark Callaghan, RocksDB Tuning Guide, github.com, 2016. MySQL 5.7 Reference Manual, Oracle, 2014. Books Online for SQL Server 2012. Microsoft, 2012. The PostGIS Development Group, PostGIS 2.1.2 Dev Manual, postgis.net, 2014. Michael Stonebreaker, Samuel Matten, Daniel J. Abadi, et al. The End of an Architectural Era. It's Time for a Complete Rewrite. At 33rd International Conference on Very Large Databases VLDB, September 2007. VoltDB Technical Overview White Paper, VoltDB, 2014. Edref, COD, S, B, COD, and C, T, Sally, Providing OLAP to User Analysts, an IT Mandate, E, F, COD Associates, 1993. Michael Stonebreaker, The Traditional RDBMS Wisdom is Almost Certainly All Wrong, Presentation at EPFL, May 2013. Daniel J. Iberi, Classifying the SQL and Hadoop Solutions, hadapp.com, October 2, 2013. Julian Ledem, Dremel Made Simple with Parquet, blog.twitter.com, September 11, 2013. Julian Ledem and Nonlai, Efficient Data Storage for Analytics with Apache Parquet 2.0 at Hadoop Summit, San Jose, June 2014. Chapter 4 Encoding and Evolution. Everything changes and nothing stands still. Heraclitus of Ephesus, as quoted by Plato in Cratylus 360 BCE. Applications inevitably change over time. Features are added or modified as new products are launched. User requirements become better understood, or business circumstances change. In Chapter 1 we introduced the idea of evolvability. We should aim to build systems that make it easy to adapt to change. See evolvability, making change easy on page 21. In most cases, a change to an application's features also requires a change to data that it stores. Perhaps a new field or record type needs to be captured, or perhaps existing data needs to be presented in a new way. The data models we discussed in Chapter 2 have different ways of coping with such change. Relational databases generally assume that all data in the database conforms to one schema, although that schema can be changed through schema migrations, i.e., alter statements. There is exactly one schema in force at any one point in time. By contrast, schema-on-read schemaless databases don't enforce a schema, so the database can contain a mixture of older and newer data formats written at different times. See schema flexibility in the document model on page 39. When a data format or schema changes, a corresponding change to application code often needs to happen. For example, you add a new field to a record, and the application code starts reading and writing that field. However, in a large application, code changes often cannot happen instantaneously. With server-side applications, you may want to perform a rolling upgrade, also known as a staged rollout, deploying the new version to a few nodes at a time, checking whether the new version is running smoothly, and gradually working your way through all the nodes. This allows new versions to be deployed without service downtime, and thus encourages more frequent releases and better evolvability. With client-side applications, you're at the mercy of the user, who may not install the update for some time. This means that old and new versions of the code, and old and new data formats, may potentially all coexist in the system at the same time. In order for the system to continue running smoothly, we need to maintain compatibility in both directions. Backward compatibility: newer code can read data that was written by older code. Forward compatibility: older code can read data that was written by newer code. Backward compatibility is normally not hard to achieve. As author of the newer code, you know the format of data written by older code, and so you can explicitly handle it if necessary, by simply keeping the old code to read the old data. Forward compatibility can be trickier, because it requires older code to ignore additions made by a newer version of the code. In this chapter, we will look at several formats for encoding data, including JSON, XML, protocol buffers, Thrift, and Avro. In particular, we will look at how they handle schema changes and how they support systems where old and new data and code need to coexist. We will then discuss how those formats are used for data storage and for communication in web services, representational state, transfer REST, and remote procedure calls RPC, as well as message passing systems such as actors and message queues.